Hello everyone and welcome back. I wanted to record a quick video focusing on the equations of two rather important surfaces in three-dimensional space, namely spheres and ellipsoids. Now, a sphere is basically a three-dimensional version of a circle. And an ellipsoid is basically a three-dimensional version of an ellipse. Now, because spheres are 3D equivalents of circle, and ellipsoids are 3D equivalents of ellipses, we can get the equations for these particular surfaces in a very easy way by just extending, basically by your first guess, extending the equations of circles and adding in an extra z term because we're now in xyz space. So let's recall that for circles, if your circle had a center of, let's call it maybe x sub c and y sub c for the center, and it had a radius of r units, then the equation of the circle would be x minus the x of the center squared plus y minus the y of the center squared is equal to the radius squared. Now, if you had to guess, if you had a sphere whose center was three-dimensional, so now we have xc, yc, and zc, with a radius of r units as well, what do you suspect that that equation will be? It'll be exactly the same thing as the circle's equation, with just one extra term. Add in the z term, z minus the z of the center squared equals the radius squared. So let's do a couple of exercises that utilize this formula. For example, someone says, find the equation of a sphere with a radius of 5 units and a center at the location 3, -2, and 0. All I need to do now is go back into this formula and plug in the radius and the point that I was given. So the equation would be x minus the x of the center squared, y minus the y of the center squared, and z minus the z of the center squared equals the radius squared, 25 from 5 squared. Now, using this formula, it is also possible to get equations of hemispheres. Hemispheres are halves of spheres. For example, I could ask you for the equation of the upper hemisphere of radius 2 centered at the origin, centered at 0, 0, 0. Working toward the answer to this problem, I'm going to note that the upper half of the hemisphere is the half where all the z values are greater than or equal to 0. So what I'm going to do is I'm going to start by building the equation of the full sphere with this radius and center. And then I'm going to solve to get the half where z is positive. That'll give me the upper hemisphere, the top half of this sphere. So starting with the full sphere, of radius 2, centered at the origin. I have x take away 0 squared, x minus 0 squared. I have y minus 0 squared. I have z minus 0 squared is equal to 2 squared. And now I'm going to try and solve this equation for z, and I'm going to restrict z to the positive values to get the upper hemisphere. Now I'll start by isolating z squared, by subtracting x squared and y squared. And then to isolate z, I would take a square root. But when I apply a square root to an equation, the square root always comes with a plus minus sign, to reflect the fact that z, technically, could either be positive or negative, and if you square it, you'll get exactly the same result. But this is the moment where I get to utilize the fact that I'm dealing with the upper hemisphere, where z is positive. And as a result of that, I'm going to isolate z and choose only the positive square root, and I'm going to ignore the negative square root. This equation, z equals the positive square root of 4 minus x squared minus y squared, would be the equation of this upper hemisphere. Now, can you imagine how the answer might be different if we were asked instead, not for the upper hemisphere, not for the top half, but for the lower hemisphere, for the bottom half? The main difference is that this time we're interested in the negative z values. We're interested in the locations beneath the xy plane. So what I would do differently is that as I was solving for z, this time I would take the negative square root to get just the negative z values, to get just the lower half of this sphere. So that is how I would find the equation of a sphere or of a hemisphere with a given radius and a given center. Now it's also possible to go backward. If I give you the equation of a sphere, I can also ask you, what is the center and what is the radius? For example, I could ask you, what is the center and what is the radius of the sphere with the equation x squared plus y minus 3 squared plus z plus 4 squared equals 3. All I have to do in this particular problem is compare the values in my equation with the values that are in the general sphere template. In the general sphere template, the number on the right-hand side of the equation is radius squared. And the numbers that are subtracted from x and y and z within the parenthesis give you the coordinates of the center. So using those principles, I'm going to look and see what number on the right-hand side do I have. That number will be equal to the square of the radius. And if the radius squared is equal to 3, then the radius itself must be equal to the square root of 3, r always being a positive number. As for the center, all I have to do is consider what values are being subtracted from x and y and z in the parentheses in my problem. Nothing at all is being subtracted from x, so the center has an x coordinate of 0. 3 is being subtracted from y, and what is being subtracted from z? I have z plus 4, which can be thought of as z take away minus 4. So the z coordinate of the center, the value being subtracted from z, is -4 units. Now, to give you a slightly more complicated version of this problem, suppose that I asked for the center and radius of the equation x squared plus 6x plus y squared minus 4y plus z squared is equal to 1. What makes this question more complicated is that this time the equation is not given to me in the standard format for the equation of a sphere. Usually, we have x minus a number squared, y minus a number squared, and z minus a number squared. But in this particular case, we have some terms containing variables that do not live inside of squares. So to fix this, I'm going to use an algebra technique called completing the square. Completing the square is the perfect technique for taking an expression like this one, x squared plus 6x, and turning into expression x plus or minus a number quantity squared. Now if I start with x squared plus 6x, the technique for completing the square is as follows. You take the coefficient on the x, you cut it in half, and then square it. So if I take positive 6 and I cut that result in half, I get the number positive 3. If I square the number positive 3, I get the number positive 9. And so what I'm going to do is I'm going to add that positive 9 into my equation. I'm going to add it in to my equation. Now when you're working with an equation, you can't just add something to one side of the equation because that will cause it to become unbalanced. So I'm adding 9 to the left side, and I'll have to add 9 to the right side of the equation as well to balance it. Now because I've added that plus 9 to these first two x terms, I've unlocked the ability to factor those terms. X squared plus 6x plus 9 can be factored as x plus 3 quantity squared. So that's why we add this plus 9 into this expression, to give us the ability to factor those three terms into something that more closely resembles what we have in the standard equation for a sphere. Now, in addition to the x terms, I will also have to do the same thing to the y terms in order to rewrite that part into something that more closely resembles a standard sphere equation. So I'm going to look at the number which is attached to y. That number is -4. I'm going to cut that in half, and that'll give me the number -2, and then I'm going to square that, and that's going to give me the number 4. -2 squared is 4. So what I'm going to do is I'm going to add 4 into this expression. I'm going to add 4 next to this expression, and when I do that on the left, I have to balance that on the right by adding 4 on the right as well. The reason that I add 4 here is because now, with that 4, I have an expression that can be factored. X squared minus 4y plus 4 can be factored as y minus 2 quantity squared. So that gives me the ability to rewrite these terms as something that is more in line with what we have in the standard equation for a sphere. So in total, what do I have? I have x squared minus 6x plus 9. I have y squared minus 4y plus 4. I have z squared, and on the right-hand side of the equation, I have now 1 plus the 9 that I added plus the 4 that I added. So in total, 14. And I did that so that I could factor the x terms, And so that I could factor, excuse me, this was plus. And so that I could factor the y terms. And the z terms are already in the right format. Now that I've completed the square for x and y, and rewritten the equation in more of the standard sphere format, I can identify the center and the radius the same way that I did in the previous problem. The radius will be the square root of whatever number is on the far right side, and the center will be the values that are being subtracted from x and y and z. So with that, we've talked about how to find the equation of a sphere, how to find the equation of a hemisphere, and how to use the equation of a sphere to identify its center and its radius. The last topic that I would like to review in this video is the topic of ellipsoids. And as noted at the beginning of the video, these are three-dimensional versions of ellipses. So just like we did for circles and spheres, let's start by reviewing the equation of an ellipse, and then let us try and extend that equation in the most intuitive, natural way into three-dimensional space. So let's recall that if you have an ellipse that has x-intercepts positive a and negative a, and y-intercepts positive b and negative b, or in other words, if your ellipse stretches to negative a and a on the x-axis, and negative b and b on the y-axis, then the equation for that ellipse was given by x squared over a squared plus y squared over b squared equals 1. Now for an ellipsoid, if the x-intercepts are, say, a and minus a, if the 3D y-intercepts are, for example, b and minus b, and if the z-intercepts are, for example, c and minus c, then your ellipsoid in three-dimensional space would stretch out to plus minus a on the x-axis, plus minus b on the y-axis, plus minus c on the z-axis, and therefore would look a little bit like this sort of egg shape here. Editor Sam, please go ahead and put a decent version of this sketch on the screen for me, please. Now, can you, based on the equation for an ellipse, guess the equation for an ellipsoid? It extends in pretty much exactly the way that you expect. You just add in an extra term, z squared over the z-intercept squared, equals 1. So for a quick example, someone says to me, find the equation of an ellipsoid, three-dimensional space, with intercepts at the following locations: plus minus 5, plus minus 6 for y, and plus minus 4 for z, then all I have to do is identify the values of a and b and c and put them into their appropriate positions in the template. And you're pretty much done. So that concludes today's material. That is how I would find the equation of a sphere, hemisphere, or ellipsoid. Now, as a quick word of caution, do be careful with the difference between these formulas and the formulas for planes that we've studied over the past couple of days. Generally speaking, when you have the equation of a plane, the x and y and z don't have any meaningful exponents. They're not squared, they're not raised to the power 3 or anything like that. The big difference here with spheres and ellipsoids is that the variables in this particular problem are being squared. So that's the big difference, I would say, between the equation of a sphere and the equation of a plane.